Welcome to CS 797K. Today's lecture, we're going to start talking about RAID levels. Before we go into the RAID levels, I want to take a brief side trip and talk about another small homework which will be assigned today. Once I find out where it went, there it is. Hamming encoding. So we talked about Hamming code in the last lecture, how to encode and decode things using Hamming code. We're adding parity bits to protect the data and find that if bits are flipped in there. So the homework we're going to do, small homework, single point, right? No big deal. Start with your WSU ID. Pick 3 or 4 of the digits in your WSU ID. Smush them together. You'll get a number. If you make sure that the number is less than 2047. If all your digits in your number are 3 or above, then you have to use 3 digits. If you got something. So anyhow, of course, 2047 is the number of bits, or is it the maximum number that can be represented with binary 11 bits. So you're going to take your number and you're going to go ahead and convert it to binary. And then you're going to make that a string in binary. So you're going to drop leading zeros and 2. You have 11 bits in your string. It's all just ones and zeros, and that's the binary representation of whatever number you picked, right? And then you're going to encode that number using the Hamming 1611 code. That's where you create a P1, P2, P4, P8, spread the data out, calculate what the values are that go into P1, 2, 4, and 8 to make those values even for each of those parity bits. And then once you do that, you calculate the number of ones in there and decide whether that leading bit, the P0 bit's going to be a 0 or a 1. You're going to encode all that. And then you're going to go into your homework once I get it posted, and your submission will be that is the string that you've encoded, right? And then I want you to go back to the spreadsheet that I'm going to post online. It's going to be a Google Docs or Google spreadsheet. And go ahead and put errors in your string and post that. And our next homework, which we're going to have points on, is going to be decoding that string. And you're going to try yourself to decode it and see if you can manually figure out what the string was. And you'll either report, I can decode this string, it's got no errors. I decode the string, it's got a single error that I was able to fix. Or this string had 2 or more bits flipped and I can't decode it successfully, right? And so that'll be the next homework we're going to do. These should be medium homeworks, shouldn't they? I'm going to post this as a medium homework with 5 points on it. Yeah. So you're going to post onto there the correctly encoded string of the number you chose and the number you coded in the correctly encoded string. We'll be grading you on that. And then you're going to flip some bits in it at random. Post those flip bits, and then we're going to use that. We're going to rearrange those randomly in the spreadsheet. We're going to assign back out to you, here's a string you need to decode, and that'll be the next homework. Should be short. Again, you can use that decode.fr webpage we talked about last time. Spend a few minutes at it yourself, try to understand it. If you get lost and confused, that's okay. We'll fix that. On the decoding, the goal is to be able to do this if you're trying to do it on an exam, for instance. So these are easy questions for us to create on the exam, and they should be easy for you to do. So that's where we're going to head on that. All right, enough of that. Back to the lecture now, RAID levels and redundancy. So we are, of course, here in our outline on basic parity. So we're going to go through just the basics of what RAID is and what parity protection is. So what is RAID? It comes from a paper, a scholarly paper by Gibson, was the main author in 1986. It was called A Redundant Array of Inexpensive Disks, a case for that, right? They later retconned it to independent disks because it turns out people that sell disk drives like to charge lots of money. So they don't want to sell inexpensive disks. They want to sell expensive disks. And RAID is kind of, hard to say with R-A-E-D, right? And here's the paper right out here. Berkeley University. This is a research paper. We can go out there. We trust berkeley.edu, right? And there's the report. What he was pointing out in this paper was that in the 1980s, the size and power of CPUs in computers and memory in computers was increasing doubling every 18 months. It's called Moore's Law. For the person who noticed this activity was happening, that things were getting so much stronger and faster in the computer business, right? He says, we're doubling our computing power every 12 to 18 months. And that means, we look forward in the future, how incredibly powerful we'll be able to see these computers. At the same time, their storage devices back in those days were these magnetic tapes and disk drives. And you could either pay just a huge amount of money for an expensive magnetic disk drive from IBM Corporation, or you could pay a little bit of money for PC drives that were being built and sold in little laptop, precursors of laptops, the IBM PC. And they would hold a little bit of data, and they weren't very reliable, and they'd break fairly quickly. And so he was arguing in this paper that, we could save people a lot of money if we could find some way to use a bunch of these cheap, unreliable drives and put our data on them in such a way that if one of those drives chokes and dies, I don't lose the data, right? So basically, just say instead of putting the data on one drive, we're going to put the data on multiple drives. We're going to copy the data around in such a way that if something's missing, I can recover it. Obviously, the easy way to do that is to buy 2 drives and write the data on both drives, right? And then as you're going through, you just, reading from both drives, verifying everything's okay. If one of the drives comes back with funky data, you've got a problem, right? If one of the drives fails, you just throw it away, plug in a new one, copy the data from the first drive, you have a mirror, right? In that case, you've got a problem that you're paying for twice as much storage as you're actually getting. So he came up with some algorithms that he described to make it cheaper. So he predicted an I/O crisis. CPU and memory sizes were growing much faster than devices at that time. He classified the existing approaches that were available in 1986 that people were already using for improving both the performance and the reliability of smaller, cheaper drives. He defined 5 what he called RAID levels. Okay, and the RAID levels were starting off with basic something that had no protection at all, and then to mirroring, and then to different kinds of parity. He calculated the theoretical performance, overhead, and reliability for each of those RAID levels. Published that. There were actually 6 RAID levels in this original paper, but one of them he just said was mirroring, so we'll get into that. Maybe I should just say he's defined 6 RAID levels. I'll just pretend I said 6. Okay, we'll fix that slide. Some terminology. IOPS stands for IOs per second. If we assume that we've got kind of a standard IO size, which is not true, obviously if you're like watching a movie, you're getting a lot bigger IOs than if you're editing a spreadsheet, right? But a simple measure of performance is just say we assume an average size of IO and how many of those can we process every second, right? Mean time to failure, MTTF, is the expected lifetime of some device. So we calculate that by taking a bunch of drives or storage devices or computers or whatever component we want to test, right? And we start sending a heavy load of data at them. And after some period of time, we say how many of these devices have failed. And we take and we flip that. The fraction of the drives that fail within time t, we take the inverse of that, and that is the mean time to failure. We're saying we expect a lifetime of 10,000 hours for this device. We expect a lifetime of 20,000 hours, right? So on and so forth, right? How long is your windshield wipers on your car expected to last before they don't clear the smudge off the windows anymore, right? Anything we have that can break, we can calculate a mean time to failure by testing a large enough sample for a long enough time. So if we have 100 drives and we test them for 2 hours, and at the end of those 2 hours we see that one of the drives has failed, we take that 0.1 divided by 2, We take the inverse of that, we get a mean time to failure, expected mean time to failure of 200 hours for these drives. Do not buy this. That is terrible, right? That's not even 10 days. That's a week, right? That's barely a week. So in reality, mean time to failures are measured in years, right? But we still do our calculations, based on this simple algorithm here. Mean time between failures. This is a term that says how long it takes before this device, before it fails twice. This is actually marketing lying to you. A failure is a failure, an error is an error. What they're talking about is how long it takes between this device to actually throw an error. Say, I've had a problem reading the data. If you try again, I can get it to you, right? So marketing. We're rolling our eyes at marketing people. I worked as a software developer at NetApp Corporation for a long time, and we always loved making fun of the people in marketing because they'd always come up with the silliest things they do. And we'll have some more marketing silly tricks in here. Mean time to repair. If you are using a RAID algorithm, you first have to notice that a failure has occurred. And second, you have to get that device that has failed and yank it out of there, plug in a new one, and then have the data from the other devices copied to it. That total time, how long it takes from the failure to having it repaired, is called mean time to repair. And those are the terminologies we're going to use in our reliability algorithms here. So the first RAID level, which was later called RAID 0, in his paper he talked about RAID 1, 2, 3, 4, and 5. But RAID 0 is striping, and he just kind of assumed this in here. But RAID 0 is you write the data across the multiple disks, right? I want to read my data faster. How can I do that? Well, instead of writing my data block 1, 2, 3, 4 on this single drive, I can buy 3 drives, and I can write the first block of file A on drive 1, the second block on drive 2, the third block on drive 3, the fourth block back on drive 1. File B, we'll write the first block here, second block here, third block here, fourth block here, and so on and so forth. These all diagrams came out of Wikipedia, in case you're wondering. They should have started with 0 because 0 relative computers, right? So a stripe is what we call this. Is the data a single stripe? And we go across before you rotate back to drive 1 again. So you can see if we want to read file A, we can simultaneously read A1, A2, and A3, right? And then we can go off and read A4. So it takes us, 2 separate reads to get that file in. Similarly for B1, if we had a file with only 3 pieces and we had it spread right, we could just do a single simultaneous read to 3 different drives and would speed up our access to that thing instead of having to read. In this case, if we wanted to read this off a single drive, we'd have 4 blocks. You have to do 4 separate reads. So it would take 4 times as long as reading a single one. So there's our stripes. With each additional disk, therefore, our performance increases. With enough concurrency, enough things going on at the same time, enough users and so on, our IOs per second, if one drive has X IOPS, then N drives has X times N IOPS. Literally, we can triple the rate at which we're reading our data with 3 drives, quadruple it with 4, so on and so forth, right? But the reliability decreases. If drive 2 fails, right, I can't read file A anymore because there's a big hole in the middle of it. And I definitely can't read file B because there's 2 big holes in the middle of file B, right? When you fail a drive in a RAID 0 like this, you don't necessarily lose all your data, but probably you do, right? The vast majority of your files are going to have some hole in the middle of it. So if a single drive's mean time to fail is X hours, N drives, your mean time to fail is X divided by N. So the more drives you add, the better your performance gets, and the worse your reliability gets. Your mean time to fail of a group is the mean time to fail of a drive divided by D. That's how we're going to report that. Another way to put that, right? So a RAID 0 group, number of drives we have. So this is the introduction to our reliability formula. This is found in the Gibson paper. In his paper, he wrote about 5 RAID levels all of which had a single drive protecting the data. So in other words, RAID 1, you'd have data on one drive, a copy on the another. RAID 2, 3, 4, 5, you'd have data on some of the drives and parity on another drive that would protect it, right? So later RAID algorithms came up with ways to do algorithms where you could handle two drives failure, so you wouldn't fail until the third drive failed, or the fourth, or so on and so forth, right? So the reliability formulas limited in what they're describing here. So here's what we have for our formula. Given D data drives in the RAID itself is divided into groups. Each group is a parity group. So that has drives in it that are protected by parity. And then there could be another group that's disjoint drives protected by a different parity. So we have D total drives, G drives per group. Therefore, the number of groups is total drives divided by G, or the number of groups. Each group has a number of check drives. In this case, it's going to be 1. And then the mean time to fail for the group is, again, mean time to fail for a disk squared, because when the first drive fails, everything's fine, right? We just keep reading the data from the remaining drives. When the second drive fails, we can't access our data anymore, right? So we have to have 2 drive failures. That's why we take the mean time to fail and square it. Then on the bottom, we take the total number of drives in our RAID volume. So G plus C, this is the number of drives in a group plus the check drives. So if we've got, say, what's called a RAID 10, where we've got a bunch of mirrors, then this is going to be 1 plus 1. And then the groups plus the check minus 1. So this is the first drive in a group to fail, second drive in a group to fail. Again, if drives fail in 2 separate groups where they're not protecting each other, it doesn't matter, right? For our calculations. In reality, it does matter, but for our simple calculations, it doesn't. We're going to ignore that. And then times the mean time to repair. So basically what we're saying is on the denominator, on the numerator, 2 drives fail. On the denominator, 2 drives fail before we fix the first one. So first drive fails, we immediately plug in a replacement. It starts copying back. As long as our copy back succeeds before the second drive fails, right? We go back to optimal condition. When that second drive fails, we're single degraded again. RAID 1 mirroring, the mean time to fail for the overall RAID. Here we go. Mean time to fail for a disk squared. This is the total number of drives in the RAID. And this is the number of drives in that group where the first drive failed. And then multiply by mean time to repair. So what are we doing here? RAID 1 is mirroring. We're going to write 2 copies of everything, right? A1, A1, A2, A2, A3, A3. The performance is the same as the slowest drive. If one of these drives is faster than the other, we're going to wait on the slowest drive to make sure we've got our data read, right? Our reliability, mean time to fail of this group is mean time to fail of a drive squared over 2 times the mean time to repair. Let's see how that fits into the formula. The overhead is 100%, or 2 times. And overhead as a percentage is how much extra do we have on top of the data storage that we would have if we just bought a single drive. And again, 100% overhead means we have twice as much data that we pay for as we actually get to use, okay? Overhead's a little weird. So RAID 10 is a non-standard RAID level, or it's something that Gibson considered in his paper, but he says, what if we take our RAID 1 and we stripe it? So here's a RAID 1, here's another RAID 1, right? We start with M drives, 2, 4, 6, 8, an even number. We create a bunch of RAID 1 volumes, and then we stripe them all together into a large RAID 0. So just as on this particular page, this one here, we stripe the data A1, A2, A3. Now, instead of doing that, each one of these is 2 drives. 2 copies of the data. Right? So we start with M drives, we stripe them to large RAID 0. Now, our read performance is X IOPS times M drives. Our write performance is X IOPS times M over 2 drives. What we're saying here is that as we're reading, we can be reading from this drive and this drive in different places simultaneously. So we have twice as many drives to read from. We could read from either mirror. When we're writing, we have to write to both of these copies of the mirror. Right? So our write performance is basically half as fast as our read performance in a RAID 10. Our overhead is still 2 or 100%. We still have 2 disk drives worth of storage, but 4 drives we've paid for, right? So we've got twice as much paid for as we have actual storage. Our reliability is the mean time to fail the RAID is mean time to fail of a disk squared over the number of drives times the mean time to repair. And we'll inspect that formula in a little bit. So again, RAID 10. RAID 1, drive 0, drive 1, data 0, 1, 2, just mirror the same thing. 4 drive, data 0, data 1, data 2, data 3, data 4, data 5. Mirrored, everything is mirrored, everything is striped acrosswise in a RAID 0 stripe. A 6 drive, data 0, 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth, right? So RAID 10 is always, you just think of it as a 2-dimensional thing with the drives in one direction, the mirrors in the other, or in this case, kind of a nested table. 2 copies of each data, striped crosswise. This is over here, group 0, group 1, group 0, group 1, group 2. So every time we add a new pair of drives, we get one more group into our RAID 10 volume. So let's check that MTTF calculation. All right, supposing we have 3 data drives in our RAID. 1, 2, 3. And 3 parity or check drives, mirror drives, 1, 3, and 5. Okay. And then in each group, there's 1 data drive and 1 check drive. And we have 3 groups. Right? We have 2 divided by 1, our number of drives in the RAID is 6, divided by the number of groups is 3, so we get our number of drives per group is 2. Yes, whatever. Anyhow, mean time to fail for the RAID is mean time to fail of the disk squared, because we have to fail 2 drives, divided by the total number of data drives plus the number of check drives times the number of groups we have. If we have 6 data drives, that's 3 check drives, or 1 check drive per group times 3 groups. One mirror in every group. We've got 3 groups in our 6 drives. So that would be 3 plus 3 is 6. This works out to the number in that next group. So this is just going to turn into a 1. And then the mean time to repair. If we look down here, we do for an M drive RAID 1, D is M over 2, G is 1, N sub G is M over 2, blah, blah. We do our mathematics, we substitute in there, and we see that terms cancel out. 1 plus 1 minus 1. M over 2 plus 1 times M over 2 is going to be M. So our mean time to fail for the RAID turns into mean time to fail for the disk squared over M times MTTR. So our formula checks out, right? So it's better than a single drive. It's better than a RAID 0, but it's not as good as it could be. That's RAID 10. So again, mirroring and striping together. RAID 2 uses Hamming code. And again, we said when we do Hamming code, right, we put a parity on bit 1, parity on bit 2, parity on bit 4. So we put parity on drive 1, parity on drive 2, parity on drive 4. We put data on drives 3, 5, 6, 7, 9, 10, 11, 12, and so on and so forth. There were only 2 products that were ever made with this technology. Back in the 1960s, IBM made what they called the 353, And in 1988, after reading the Gibson paper, a company called Thinking Machines says, "Ooh, that sounds good. We'll go ahead and do that," right? Even though IBM had already discontinued theirs for reasons that are apparent when you think about the other algorithms that are in there. It is considered obsolete, but I did find a picture. This is a Thinking Machines data vault. It was full of inexpensive drives, right? It stored 5 gigabytes worth of data. That's like one little tiny corner of this phone here, right? Yeah. So huge, 5 gigabytes. It contained 39 disk drives, right? 32 of them were data, 7 of them were parity. So it's parity 1, 2, 4, 8, 16, 32, and 64. Oh, 32, I'm sorry, 32. And then the other drives were data drives. It split the data into 32-bit words. It added a parity, and then it wrote those to the disks. So that was a Hamming 39, 32 with 4. So they actually had an overall parity, P0, to see if there was an error in there, so they could actually do error detection on the fly if there was a bit flipped in one of the drives, right? But RAID is designed to protect against device failures, so that wasn't really as important to them. So they had 6 parity bits, needed 7 parity bits, blah, blah, who cares? So there's an overall parity bit to Hamming says 4. The photo caption, this is funny, on the Wikipedia, says there are actually 42 drives in that box, which tells us they were actually putting hot spare drives in there. So if there was a failure, the box would detect it and immediately start recreating the data on another drive, right? So Hamming code was useful in data storage for a while. Again, as we talked before, Hamming code still is useful in main memory on computers. And there's a modified Hamming code in place on solid state drives. So it's never going anywhere. It's always part of the underlying basis of our computers, right? RAID 3 has a single check disk. This is a byte level encoding with n data disks and 1 dedicated parity. The disks are synchronized. All reads and writes are required to be full stripe. Performance is about that of a single drive if the IOs are large enough. The reliability, the mean time to fail, we have to fail 2 drives. We have to fail any one of these drives and any second drive before we repair the first one. That's when we would expect to see the whole thing fail. Our overhead is n plus 1 over n. In other words, we've got 3 data drives, but we've bought 4 drives. So our overhead in this case is 4 over 3, or 33%, right? Overhead. RAID 4 is very similar to RAID 3 in its layout. It does block level encoding instead of byte level encoding, which means that it can write things at the same time. It uses a read, modify, write algorithm. So if I want to update this block, what RAID 4 does is it reads in this whole stripe. It recalculates what this P over here should be, and we'll get into what that is in a moment. And then it writes out A2 and AP. It doesn't have to rewrite this data because you didn't change it, but it has to do this read, modify the data in memory, and write it back out. That has to be an atomic operation. That causes all sorts of interesting problems. So the large write performance is about that of a single drive. In other words, we're writing something, we have to write all those drives at once. Our random small write performance, if we want to update this little piece, we have to read all those 4 drives in, modify them, and write half of them out. So it's not very good. You have to go out and buy cache memory to do all your work in cache. Your read good performance is really pretty good. You want to go out and read something, you can read any one of those drives, or where your data is, right? So you can be reading from all these simultaneously. Your parity drive, if you have a lot of writes, you have to keep recalculating that parity. That can turn into a bottleneck, cause you performance issues. Your reliability is the same as RAID 3 because it's the same physical layout. Your overhead is the same as RAID 3. This was the basis for what's called the NetApp File Attached Storage System, released in 1992. NetApp Corporation, of course, we're in the corner here at 17th and Oliver. That was their flagship product for many years. They are, in fact, still selling FAS. They've got better algorithms now, more redundancy. They've got all sorts of features they put on top of it, but there's still this RAID 4 algorithm laying down there in the guts of every NetApp FAS box out there. How does read, modify, write work? Well, the first thing we have to recognize is what that drive that's labeled A sub P and B sub P. P means parity, and we're doing an XOR. We're calculating a parity on there such that that entire stripe has even parity for any particular bit position relative to the same. So block 0 on this drive, bit number 314, and block 0 bit 314 on this drive, and block 0 bit 314 on this drive. And same thing on here. If we add all those up, we get a 0. If there's a 1 here, a 1 here, a 1 here, we'd put a 1 here. If there's a 1, a 0, and a 1, we'd put a 0 here, right? So we're writing the parity at AP. So to read, modify, write the data, we want to write to drive new, drive 1, drive new 1. We want to take drive 1 here. We want to update the data right here, right? So what do? We start by read D1 and P from the media, both of those drives, just those two. That's all we need. We subtract D1 from the parity. So we basically calculate a new parity where the parity is the existing parity XORed with the data that's currently on drive 1. Now we take the new data and we add it in using the same operation, XORing, because XOR is the same as subtraction and multiplication, right? You've only got 2 bits in binary. Adding and subtracting are going to be the same operation. So we add the new data, and again, by doing an XOR, now we take our new parity and our new data, and we write them out to media. So we've updated that. So we've done, instead of doing a single write, if we had a basic drive we've got there, we've done 2 reads and 2 writes. Right? So you get some multiplication on there. RAID 5 is the same as RAID 4, but our parity rotates. RAID 4, because the parity is on the same data. If we're doing a lot of writes, we're always out there calculating the parity writing to that drive. If we rotate things around with RAID 5 like this, now if we're writing file D and file A, we can be calculating the parity, and we can be writing that in such a way that we have less overlap between the other data. So, you know, if we had RAID 4 and we were updating A and D, we'd have to do 2 writes to drive 3. In this case, we'd have to do 2 writes to drive 0 and 1, but it spreads out, whatever. Yeah, it's got a better performance than RAID 3 or 4, but if you've got a sufficiently large cache, it doesn't matter. Your read is X IOPS, that's N data drives. Your write is approximately that of the slowest drive. Your reliability, again, single drive failure, therefore the formula is the same as RAID 3 and RAID 4. Your overhead is the same as RAID 3 and 4. This was an NCR product, NCR E-Series, released in 1991. It's also a company called EMC Symmetrics, released in 1992. I was working at NCR when they released the E-Series. NCR later got bought by NetApp. So NetApp actually sells 2 different competing types of RAID algorithms. They sell the RAID 4, they sell the RAID 5, right? So they had 2 different products. They kind of combined them into a single line, product line, but you know, we'll see how long it lasts. So RAID 4 versus RAID 5. Again, RAID 4, data 0, 1, 2, 3, 4, parity. 5, 6, 7, 8, 9, parity. 10, so on and so forth. Here, parity simply rotates the data on each stripe is the same amount. It's just rearranged on different drives. So when we're starting to read the data, with RAID 4, we're only reading from these first 5 drives. With RAID 5, we're reading from all 5 drives simultaneously, depending on where the data is coming from. In some cases, parity is over here. In some cases, it's over here, so on and so forth. So in general, we're able to read from more drives. Our performance is slightly better than RAID 4. After Gibson, people started looking at this. Some people, like thinking machines, decided they were going to release something based on something that was in the paper. Other people says, you know, we can have more redundancy. We can have nested RAID levels. We can have non-standard RAID levels. So briefly going through these, RAID 6 is any RAID that can tolerate 2 disk failures. How do we do that? We have 2 different parities, P and Q. Now, just like with when we went to the Hamming code, we can't just add another parity bit and expect it to help, right? If we, well, in this case, yes, it can. We're not trying to fix the data. We're trying to recover the data when something fails, right? So if we have A1, 2, 3, and 2 parity drives, and one of these drives fails, we can recover from the parity. If one of the parity drives then fails, we can still recover it, right? So we have a little bit more reliability. In order to get full advantage of reliability, we have to make a different kind of calculation, use something that's not just a simple parity calculation. It's called a Reed-Solomon PQ syndrome parity. Or we can rearrange these parities in a different order such that there's the parities are in different places. They protect different data blocks using row diagonal parity, or what's called even odd. Our reliability now has gone beyond the Gibson paper. Now we have to fail 3 drives. So the numerator of our fraction, which is a good thing, a big numerator, just got a lot bigger. We take the mean time to fail of a drive, we cube it now, right? So instead of, you know, 10 by 10 being 100, now we got 10 by 10 by 10 is 1,000, right? So gone up another order of magnitude on our reliability on the numerator. The denominator now is also a little bit bigger, though. We've got total number of drives in the group, 3 data drives plus 2 parity drives, right? So n is the number of data drives, n plus 2, n plus 1, and n. So if any one of those 5 drives fails, we're fine. If a second drive fails, we're fine. If a third drive fails, we're dead. As long as we get this thing repaired before that third drive fails, everything's cool. We're still running. Okay? RAID 7 is a terminology, triple parity and beyond. You know, can we survive 3 drive failures so that our failure only occurs at MTTF to the power of 4, right? Not necessarily standard naming. The Storage Networking Industry Association calls this RAID 6 triple parity. We're going to use the terminology RAID 7.x. 7.1 means we can handle 1 drive failure. 7.2 means we can handle 2 drive failures. 7.3 means we can handle 3. 7.4 means we can handle 4, so on and so forth. It gets a little ridiculous when you have too much redundancy, but it's theoretically possible. Implementation details vary. You can see here, RAID 5 and RAID 6, right? And, you know, why didn't they just go RAID 7, RAID 8, RAID 9? Because eventually they run into RAID 10, which they already was taken, so they can't handle the redundancy, so they had to do some kind of way to change the numbering. So our standard implementation, what I think of as the NCR implementation, the Wichita implementation that we did right here in Wichita, Kansas, we call PQR parity, where we take the PQ parity, which is called Reed-Solomon coding. We'll get into that later. And we add an R parity. And with Reed-Solomon, you can go PQR, PQRS, keep adding letters until you run out of alphabet, right? And you have just more and more redundancy. There is a product called the ZFS file system. And I'm working on trying to figure out how to install that on a Linux box so I can make you all do it in the class for a homework assignment or a project. Implements RAID 7 in software. They call it RAID Z or RAID Z. There are no hardware products. because when you start calculating this R parity, you have to do a lot of overhead calculations. You have to have a lot of hardware or take time. Reliability of a RAID 7 triple parity, you have to fail 4 drives. First drive, total number of data drives plus 3. Those are 3 parity drives total, P, Q, and R. We've failed 1 drive. Now we've got 2 remaining. We've got failed the 3rd drive, so on and so forth. So we've got to fail 1, 2, 3, 4 drives after that 4th fails. If we have not reconstructed it in time, then our volume group is dead. Not nested RAID. We already talked about RAID 10, where we mirror a RAID 1 and then stripe the mirrors. You can also do a RAID 50. We make a RAID 5 volume and then stripe 2 RAID 5 volumes together in a RAID or 4 or 3 or 4, whatever RAID volumes striped together as a RAID 0. Someone released a product once called RAID 0+1, which when I heard about this, I was really surprised because someone had basically misunderstood how RAID 10 was supposed to work. Instead of mirroring the data and then striping the mirrors, they striped the data and then they mirrored the stripes. And this sounds like it shouldn't make any difference. In fact, what they did was, if a stripe failed, then that entire mirror was dead. So if they had a 6-drive RAID 0+1 and 1 drive failed, suddenly they were running a 3-drive volume, because like they either took down, all 3 of the drives, or it took down the other half. So I don't know. It was weird. RAID 6 on top, or RAID 0 on top of RAID 6 can have another nested one. Other non-standard RAID levels. We talked about how you can stripe things and you can do mirroring, but do you have to have an even number of drives? Well, some companies came up with a notion. They says, no, you can have any number of drives. Here's a RAID 1E, RAID 1 scattered. You can see there's two copies of RAID drive data A. There's 2 copies of data B1. There's 2 copies of data A2, and so on and so forth. They're just smeared across 3 drives, right? So that's a way to get a little bit better performance without much added reliability, unfortunately. RAID 5E, EE, and 6E, basically, all this is saying we have a hot spare drive. We put an extra drive in there. We keep it spinning at all times. If a drive fails, we immediately start the reconstruction on that drive in order to get the data revived quickly. RAID Z, of course, is the software. The cool thing about RAID Z is that it can have a different number of drives as you go through. So if you have big drive and a little drive, you can mirror them up until it gets to the end of the big drive, and then you can have just a RAID single volume after that, right? Another RAID we'll call RAID diagonal parity or RAID double parity. And this is a RAID 6 algorithm. We've got a P drive and a DP. This is a RAID 4 or RAID 4 parity. This is one of those marketing slides. It's using arithmetic. It says 3 + 1 + 2 + 3 is 9. Of course, marketing people don't understand how XOR works, or they think the customers don't understand how XOR works. So they made this with simple decimal arithmetic. So they basically just add these things up. 1, 1, 2, 1 adds up to 5. 2, 3, 1, 2 adds up to 8. 1, 1, 3, and 2 adds up to 7. And then we create these diagonal stripes. 3, 1, 1, 2. Add those together, we get 7. 1, 2, 2, 7. We add those together, get 12. Now, each of these blocks of data is protected in 2 different directions: a horizontal protection and a diagonal protection. So we can actually recover from two drive failures by rebuilding things through a chain. We'll get into that in our next lecture. Another non-standard RAID level. Yes. Anybody still awake out there? I go to these lectures. I'm like, I worked with this for like 30 years. I think this is cool to me. And everybody goes like, why are you wasting our time with this? I understand. The point being, this all still exists. This is all still out there. This is not going away. It's going to change form into something else. But there is a certain type of job that if you want to get it, you need to understand this stuff. If you don't want that job, I don't know why you're in this class. Hopefully I'll interest you enough that you want to go out and try to get that kind of job. This is a dynamic disk pool. This is a RAID 6 PQ Reed-Solomon. And instead of being 10 drives, it's got 24 drives. And it takes a simple 8 plus 2, that is 8 data and 2 parity drive, RAID 6, and it randomly, semi-randomly scatters it on those 24 drives. So you see there's an orange. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 orange blocks. There's 10 red blocks, 10 blue, dark blue, 10 light blue, so on and so forth. And all this is doing is taking your data for a simple RAID 6 and scrambling it around in a bunch of drives. So what happens if this drive fails, right? We can immediately reconstruct all 4 of these blocks basically at the same time, right? We don't have to count through in a linear fashion. We can start reconstructing this drive off the blue drive. So we do a read to those. We'll have overlapping reads, but it won't be the same thing. They'll be able to do reconstruction a lot faster. So they get a lot more reliability out of this simply by having more drives, being able to reconstruct the data much more quickly than if they had it in a standard 10 drive wide RAID 6 volume. What? Yeah, there's only 3 data blocks on there. There's 5 down here. Oh, the green. 1, 2, 3, 4, 5, 6. Well, they've got a drive failure in there someplace. That's interesting. I hadn't noticed that. Thank you. Who hired you? Interesting, interesting. Okay, so yeah, if you find any other errors in it, this is what we call a marketing slide. I stole it off the NetApp marketing page, describing how RAID dynamic pools work. And yes, there's no guarantee. What we're going to say is we have had a drive failure, and it is in the process of rebuilding the data, and it simply hasn't finished rebuilding that green data piece yet. You can look at the other colors, tell me what other ones haven't finished. There you go, okay. Troublemaker. Limitations of RAID. RAID is an erasure coding. Remember in the Hamming code, we said if we had a single bit flip, we could correct it. This sounded attractive to people. It says I'm going to make a RAID 2 volume because they say, well, if there's an error in reading, I can fix it. Unfortunately, you can't fix a dual bit flip, right? But RAID was conceived as erasure coding, not I'm going to fix errors as they go by. It is if I cannot read this bit, I obviously that it's wrong, and I'm going to rebuild it from the remaining drives. I'm going to trust the drives are giving me good data. They're not giving me errors. So it recovers from drive failures. But if you get an error, if a drive returns a 1 when it should return a 0, you're going to get corrupted data with standard RAID algorithms. Right? Now you can put things in there to scrub the data, check it. With RAID 6, with RAID 1, you can tell if there's a problem, right? But you may not be able to fix it. You have to do atomic writes. Remember, we talked about a read, modify, write before. Read, modify, write means, you're working in cache. You're changing the data. You're writing it back out to 2 different drives. If the write succeeds to drive D1, and then everything crashes, the power fails, and the write doesn't go to that parity drive, now you've got corrupted data on that stripe, right? So you have to make sure that your calculations are protected. If there's a power failure, you have to store it in like a write-ahead log, like a database. and pick it up and finish it or roll it back after you power up. I can still remember a customer problem where they had data corruption, and it turned out it was due to a power failure. And we started doing failovers, and that power failed at just the wrong time, and we had a hole in our algorithm, and we didn't get that atomic write accomplished. And that was a whole deal. That was a whole deal, because they depended on us to get this right. We fixed that quickly. It doesn't protect against accidental or malicious deletion. All right, you can always go out there on your Linux box and type rm-r/, rm-rf/, and it will delete every file on your computer. The operating system will slowly disappear out from under you. You can also do that in your MacBook if you want to. You have to use PowerShell on Windows for a similar. I was going to do a Linux virus. Run this batch file; it'll delete your operating system. Warning, warning! This is a virus. Don't run this. Right? So yeah. Anyhow, so backups will always be necessary. There's actually a YouTube song out there where someone said you need 3 copies on 2 media and 1 offsite. So your data, you should always have 3 copies, whether you got RAID or not. Right? Your RAID can make 2 copies or 3 copies, but you should have another copy on a different kind of media. Right? Because someone can go out there and maliciously delete the data, or as once happened with Hewlett-Packard, they can accidentally update their software while a backup is in progress and end up deleting the data instead of backing it up. And 1 off-site. You should always recognize that meteor strikes can happen. Wars can happen. Power failures can be long-term power failures can happen. If you have precious data that needs to be preserved, then you need to make sure you have a copy elsewhere. And if anybody gets a chance to go tour the salt mine up in Hutchinson, you should take the advantage and go. It's called Stratica, and they have data storage in a 600 feet, 200 meters underground. It's pretty cool. Yeah. Limitations of RAID more. Performance characteristics vary widely with the I/O pattern. If you're doing small I/Os, it doesn't go as fast as if you do large I/Os. If you start doing random I/Os, it doesn't do as well as sequential. Drive failures are not always independent. If a drive fails, spinning media, this is getting old now, right? None of our laptops have a spinning disk in them. But it used to be the case, you'd drop your laptop and all your data was gone because the hard drive would crash when it hit the ground. Now you've got solid state drives in there. Solid state drives are not susceptible to this, but spinning drives are. The head can start vibrating as it's crashing. And then it can cause all the drives next to it to start vibrating. It can bring down a cascade of drive failures. So we always would tell people to arrange their data vertically so that you don't have 2 drives right next to each other that had your data on them. Right? And of course, a power outage is going to take everything out at once anyhow. Higher capacity drives, new technology drives. Again, RAID 6 was invented because it took too long to reconstruct a RAID 5. You can't get your data correct. There's huge drives. It would take so long to rebuild 1 drive. RAID dynamic disk pools were done so you wouldn't have to reconstruct an entire drive, right? So, and then solid state drives have their own internal error detection and correction using Hamming codes. And do you really need extra redundancy? So again, is it still relevant? I had to put this up in this slide because at some point, maybe RAID will not be relevant. And you'll be sitting there going, I wish I hadn't wasted my time taking that CS797K class. But I think you'll learn enough stuff in there that you'll find it useful because we got basic concepts anyhow. So credits and further reading, I will just put those up here for your perusal later. The original RAID paper, images off of Wikipedia. Here's another lecture where they do some RAID lectures. I have no idea if all of these are still valid. This is an entertaining video right here. Someone's demonstrating about how you can induce errors on a drive. He would go up and yell at the drive, make it vibrate. And here's when my daughter sent me this video about computer science being the worst major. If that's a joke, if it's still out there, we'll see. Okay. Bitwise operators, We did that again. Reminders, XOR is a parity calculation, right? We're XORing parities together such that if there's an odd number of bits, the XOR result is a 1, and that gives you even parity overall, or parity is calculated as the number of bits modulus 2. End of lecture. Time 1:37. While I'm pulling this up, I'll ask if there's any questions. No questions? And we can go ahead and bring up our attendance for today. Should we do tomorrow's attendance or Thursday's attendance? No, I haven't even looked at this quiz. All right, so before we do that, we're going to go out here. We're going to stop the recording. We're going to stop.